Hey everyone, in our last video we learned what the JVM is and how it powers Java's famous write once run anywhere promise. We also saw that our Java source code is compiled into bytecode and the JVM executes that bytecode on any operating system with a compatible JVM. But have you ever wondered what actually happens inside the JVM after you click run? How does it find your classes? Where does it store objects and variables? How are methods executed? And how does Java automatically manage memory without us manually freeing it? To answer all these questions, we need to understand JVM architecture. By the end of this video, you will have a clear mental model of how the JVM works behind the scenes. This is also one of the most commonly asked Java interview topics, so let's make it simple. Before diving into the technical details, let's first look at the big picture. Imagine the JVM as a highly organized factory. Whenever you run a Java program, this factory has three major sections. To visualize this better, I have recreated a standard JVM architecture diagram based on the official JVM specification. The class loader subsystem is the entrance of the factory. Just like raw materials enter a factory before production begins, your Java class files enter the JVM through the class loader. Next, we have the runtime data areas. Think of these as the storage rooms of the factory. Different types of data are stored in different places so that the JVM can quickly access them whenever needed. Finally, we have the execution engine. This is the heart of the factory. It takes the loaded classes, executes the bytecode, optimizes performance, and works with the garbage collector to manage memory. If you remember this simple factory analogy, understanding the JVM architecture becomes much easier. Now let's explore each of these components starting with the class loader subsystem. Whenever a Java program starts, the JVM first needs to locate the required .class files and load them into memory. This is the responsibility of the class loader subsystem. One of Java's powerful features is dynamic class loading. Instead of loading every class when the application starts, the JVM loads a class only when it's first needed. This improves startup time and uses memory more efficiently. The JVM uses three built-in class loaders to load classes. The first one is the Bootstrap class loader. It has the highest priority and loads the core Java libraries such as java.lang, java.util, and other fundamental classes that every Java application depends on. Next is the platform class loader. It loads the standard platform libraries provided by Java. If you are learning from Java 8 or older resources, you may see it referred to as the extension class loader. Finally, we have the application class loader. This is the one you will interact with the most because it loads the classes that you write in your own project. Now you might be wondering, how does the JVM decide which class loader should load a class? Since there are multiple class loaders, the JVM needs a way to decide which one should load a particular class. The answer is the parent delegation model. Whenever a class loader is asked to load a class, it first asks its parent loader to try. If the parent successfully loads the class, the process stops there. Otherwise, control returns to the child class loader, which then attempts to load the class itself. This approach prevents the same class from being loaded multiple times and improves security by ensuring that core Java classes are always loaded from trusted sources. If a required class cannot be found, class loading fails, which may result in a class not found exception or no class def found error, depending on the situation. Once the JVM finds a class, it still isn't ready to use immediately. Every class goes through three important phases before it can be executed: loading, linking, and initialization. Let's understand each of them. The first phase is loading. Here, the JVM reads the .class file and creates an internal representation of that class inside the JVM. Next comes linking, which prepares the class for execution. Linking has three steps. The first step is verification. The bytecode verifier checks whether the bytecode is valid, type safe, and follows JVM security rules. If verification fails, the JVM throws a verify error. The second step is preparation. During this step, memory is allocated for static fields and they are assigned their default values such as 0, false or null. The final step is resolution. During this step, the JVM resolves symbolic references into direct references that it can use efficiently during execution. Finally comes initialization. During initialization, static variables receive the actual values you have assigned in your code, and any static blocks are executed in the order they appear. At this point, the class is fully initialized and ready to be used. So now we have seen how the JVM locates your classes, loads them, verifies them, and prepares them for execution. But once everything is loaded, where is all this information stored? To answer that, let's move to the next part of the JVM architecture, the runtime data areas, where the JVM organizes memory while your program is running. You can think of this as the internal memory layout of the JVM, where everything has its own dedicated space. Some parts are shared across all threads and some are private to each thread. Let's go through them one by one. The first area is the method area. This is a shared memory area where the JVM stores class level information. It contains class metadata, method information, runtime constant pool, and static fields. You can think of it as a place where the blueprint of our classes is stored. Since multiple threads may need access to the same class information, this area is shared across the JVM. In modern Java versions, this area is typically implemented using Metaspace. Next is the heap area. This is one of the most important parts of JVM memory. Whenever you create an object using the new keyword, that object is stored in the heap. For example, employee emp is equal to new employee. Here, the employee object is created in the heap, while the reference variable emp is stored in the stack frame of the current method. The heap is also shared across all threads in the JVM, and it is the main area managed by the garbage collector. When objects are no longer reachable by the application, the garbage collector reclaims their memory. Now let's move to the stack area. Unlike heap, the stack is thread specific, meaning each thread has its own stack. Whenever a method is called, the JVM creates a stack frame. This frame stores method specific data like local variables, method parameters, and intermediate result. If method A calls method B and method B calls method C, each call creates a new stack frame on top of the previous one. When a method finishes execution, its stack frame is removed automatically. If the stack grows too deep, for example due to uncontrolled recursion, the JVM throws a stack overflow error. Next is the program counter register. Every thread has its own PC register. You can think of it as a small tracker that keeps track of the current instruction being executed. It ensures that when a thread resumes execution, it knows exactly where it left off. Finally, we have the native method stack. This is used when Java calls native code written in languages like C or C++. Whenever a native method is executed, its information is stored in this separate stack area. Now let's quickly summarize the memory model because this is very important for interviews. The heap and method area are shared among all threads, but the stack, PC register, and native method stack are private to each thread. This separation helps Java to support multithreading safely and efficiently. So now we understand how memory is organized inside the JVM. We know where objects are stored, where method calls are tracked, and where class information lives. But all of this memory is useless unless something actually executes the code. That's where the execution engine comes in. You can think of it as the processor of the JVM that takes bytecode and executes it step by step. It mainly works using three components. The first one is the interpreter. The interpreter reads bytecode instructions one by one and executes them immediately. This makes the program start up fast because execution begins right away. But there is a drawback. If the same code is executed again and again, interpreting it every time becomes slow. So while the interpreter is simple and fast to start, it is not the most efficient for long-running applications. To solve this problem, the JVM uses the just-in-time compiler, also known as the JIT compiler. The JIT watches your program while it runs. If it notices that a particular piece of code is being executed frequently, something called a hotspot, it may compile that bytecode into native machine code. Once compiled, that machine code is reused directly instead of interpreting it again and again. This significantly improves performance, especially in long running applications. This is one of the key reasons why Java gets faster over time while the program is running. Next, we have the garbage collector. The garbage collector is responsible for automatic memory management. It runs in the background and looks at objects in the heap. If an object is no longer reachable from your program, it is considered unused and the garbage collector reclaims that memory. This is what allows Java developers to avoid manual memory management like in languages such as C or C++. Now, sometimes Java needs to interact with code written outside the JVM, usually in languages like C or C++. For this, Java provides something called the Java Native Interface or JNI. JNI doesn't contain native code. Instead, it acts as a bridge between Java code and native libraries. These libraries are typically written in languages like C or C++ and provide platform-specific functionality. Whenever a Java program needs to access operating system features or use existing native code, it communicates with these libraries through JNI. Now let's quickly connect everything together and understand the full flow. When you run a Java program, your source code is first compiled into bytecode, then the class loader loads the required classes into the JVM. After that, the runtime data areas organize memory, objects go into the heap, method calls go into the stack, and class metadata goes into the method area. Finally, the execution engine begins by interpreting the bytecode and uses the JIT compiler to optimize frequently executed code, while the garbage collector continuously frees unused memory. So, if we summarize JVM architecture in three simple parts, the class loader loads your classes, the runtime data areas manage memory, and the execution engine executes your code. That's the complete picture of how the JVM works internally. Once you understand this flow, Java stops feeling like a black box and you start understanding what is actually happening behind your code every time you run a program. In the next video, we will set up the JDK, configure environment variables, and finally write our first Java program from scratch. If you found this explanation helpful, make sure to like the video, share it with your friends, and subscribe for more Java tutorials. And let me know in the comments, have you ever faced a Stack Overflow error while coding? What caused it? Thank you for watching. Keep learning, keep growing, and stay connected for more updates.